In this video, we discuss first order logic. So what is first order logic? We'll go through this. Logic we have discussed, basically inference, infer new information from some given information or knowledge, or try and discover what caused certain information to be deducted. So like going backwards, trying to find out what caused something. And this then represented in logical form makes life a lot easier when you're trying to reason about normal real life things. Start with atomic sentences. Atomic sentences are the most basic elements of first order logic. Okay, these are formed from a predicate symbol followed by a parenthesis with the sequence of terms or items that are passed on. People who are familiar with CS can look at it as a function. So function with some parameters. Okay, so we can represent atomic sentences as predicate, as said, some predicate name, terms 1, 2, 3, 4, whatever you want to call it. Okay, so for example, Ali and Ahmed are brothers. So you'd say brothers, that's a predicate. Within parenthesis, Ali, comma, Ahmed. That's a very simple representation. Chinky is a cat, Bubbles is a cat. So you can say cat, bracket, Chinky, comma, Bubbles. So here, both brothers and cat are predicates. And as you can see, very simple statements, and they can be represented in mathematical form. Of course, there are complex sentences made out of this. So combining these atomic sentences and or not whatever, you can represent complex sequences, complex sentences, and so forth. All right, so first order logic statements can be divided into two parts. Okay, there's a subject, which is the main part of the statement, and a predicate. A predicate, as I said, can be defined as a relation which binds two atoms together in a statement. For example, I said consider x is an integer. Okay, it consists of two parts. The first part is x, which is the subject and the statement of the statement, and second part is an integer that's known as a predicate. So integer is a predicate, and that's where the term predicate logic comes from. Now, moving forwards, there are certain requirements when it comes to general statements in general, and then you want to do computing part of it. And here I repeat what I've been saying before. AI is trying to replicate, computerize human thinking, human reasoning. Okay, so that's the back of our mind, and this is why we're trying to put these things together. All right, so in first order logic, you've got something called a quantifier. A quantifier is a language element which generates quantification. Okay, and quantification specifies the quantity of a specimen in the universe of discourse, wherever we're talking about. We're talking about medical domains. That's our universe of discourse. In general, the world across, the globe, yes, that's also our universe of discourse. In software engineering, you have those concepts. So that becomes your specific quantifiers within that context. And so these are symbols that permit us to determine or identify the range and scope of the variable expressed in the logical expression. And there are two types of quantifiers mostly used. One is a universal quantifier, meaning something that applies to everyone. Okay, so there is a particular symbol used for that, which is an inverted A. So this universal quantifier can specify that all humans, if we were to represent that, all humans are mortal, right? So you would need to use this universal quantifier. We'll see examples of this. The other one is called the existential quantifier. coming from the word existence. Something exists, okay? That's where the term comes from. So existential quantifier. And this is represented typically with an inverted capital E, and really means for some, okay, something, or at least one. Okay, so that's existential. Universal means for everything. Existential means for some, at least one, or some part of that. The universal quantifier is a symbol of logical representation, which specifies that the statement within its range is true for everything or everyone, every instance of a particular thing. And I said it's represented with an inverted A. The universal quantifier, we use the implication, okay, the arrow. Remember, P implies Q somewhere else I mentioned. So if X is a variable, then this universal quantifier, inverted A of X, this means for all values of X, for each value of X, for every X. That's what it means when we say for all values of X. So in the diagram, we've tried to represent a few things. For instance, on the left hand side, you notice, there's somebody called X1, that's a variable, drinks coffee, okay? And X2 drinks coffee, X3 drinks coffee, and so forth. Xn drinks coffee, a number of these people. And on the right, you see a universe of discourse, men, or called man here, right? So from there, we are picking up that, X1, X2, Xn, they drink coffee. Now, in the shorthand notation, we can write it as for all values of X, where X is a man, right, represented as man is a predicate within X. So for all values of X, where X is a man, implies that X drinks coffee, and that drink itself is a predicate which takes two arguments: X, which is a representation of a man, a person, and with coffee. So it can be read as for all men drink coffee. That's what it is. I say that again. There are all X, where X is a man who drinks coffee. So in short, all men drink coffee. Of course, there are exceptions, but that's what it says. Right. The existential quantifier. Remember the word coming from existence. The flipped capital E. So capital E are the type of quantifiers which express that the statement within its scope is true for at least one item, one instance of that. So you could say if at least one person drinks coffee, one man, you would use this flipped E to represent that. Okay. And when it is used with a predicate variable, then let's say existential E with N, it is called an existential quantifier. Quantify means it puts a number to it. And in this existential quantifier, we normally always use the and or conjunction symbol, which is an inverted V. Okay. Now, if X is a variable, then existential quantifier will be this E of X, or E within brackets X, existential X, and it will be read as follows: there exists an X. Okay, this is how it will be read: there exists an X, or for some values of X, or for at least one X. This is what it means. Okay, it could be almost all of them, but you say at least some of them, or at least one, which satisfies whatever we're talking about. Let's look at this. For all values of existential X, boys X, and intelligent X, this will mean there are some X where X is a boy, and the word boy is taken from that predicate, boys X and intelligent X. So there are two predicates. So what does this statement mean as you written here? There are some X where X is a boy who is intelligent. Okay. So some boys, in other words, some boys are intelligent. So this is a normal statement which we normally use. But in predicate logic form, this is how you will represent this. And then we can argue, computer can actually argue and process this information, for which we don't really do it. We do it symbolically. Okay, now the points to remember. The main connective for the universal quantifier, of course, is inverted A and with an implication. For existential quantifier, it is capital E inverted and the and connective, the main connective there. These are the two basic things. All right, some examples of first order logic using quantifiers. All birds fly. All birds fly. In this question, the predicate is fly bracket bird. Okay, so the fly is the predicate, the real predicate here. And since there are all birds actually fly, so it will be represented in computerized forms as for all values of x, where x is a bird. So you will say for all values of x, space bird bracket x implies that bird will fly. So another predicate, a bird predicate and a fly predicate. So all birds fly. This is what we're trying to represent. And this is how simple it is. But remember, there are some flightless birds as well. Some birds that don't fly, okay, like ostrich and others. So what I've discussed so far, and this is where I'm going to close up, normal statements that we talk about freely and understand, right? But if we are to computerize them for the sake of artificial intelligence and being able to infer new information or discuss or build on the logic, we need some kind of a representation which is first order logic. Of course, there are other logics there, but this is what we're going to, where we're going to stop and give you an idea how it works. I hope you enjoyed this. Thank you very much. We'll see you next time.